Suppose X follows the normal distribution with mean mu and variance sigma squared. The maximum likelihood estimator for population variance sigma squared is given by sigma hat squared, which is the mean of the individual xi's minus the sample means squared. The theoretical bias of this maximum likelihood estimator, theta hat squared, is given by the bias of sigma hat squared, which is equal to negative 1 over n sigma squared. Last time, we used Bootstrap to approximate the bias of the MLE. So this time our question is, how can we implement this using Jackknife? And what does the Jackknife bias estimator give us? Just like last time, we'll still consider a sample size of 25, and without loss of generality, assume X follows the standard normal distribution with mean 0 and choose sigma squared equals 1. Under this setting, we can plug in the n and sigma squared here, and we can see that the true bias of our MLE is negative 0.04. To implement the Jackknife bias estimator, we will need to first compute the theta hat i's, the theta hat using all 25 samples. This is the estimator computed with the entire sample. Nothing is left out. In step 2, for each I between 1 and n, here n is 25, we will compute the theta hat with xi left out. So that is the theta hat i's in our slides. And then after we get the leave one out estimators, we have a total of 25 of them because our n is equal to 25. We can compute the mean of these leave one out estimators, which is given by theta hat bar. In the last step, we can compute the bias estimate using Jackknife, and that's given by n minus 1 times theta hat bar minus theta hat. So here's the code that implements this. We first generate a total of 25 samples from the standard normal distribution. Then we first compute the theta hat, which is the MLE using the entire 25 samples. We will then create a zero vector of length n called theta I, which we will use to store each of the theta hat i's. In other words, the leave one out theta hat estimates. For I between 1 and n, the ith entry of theta hat I will be given by the MLE computed with the ith observation left out of x. So x, excluding the ith observation, can be obtained in R by doing x bracket negative I. This tells R that you are going to exclude the ith observation or the ith entry of a vector or a matrix from your subsequent operations. In the end, the bias estimate using Jackknife is given by n minus 1 times the mean of the theta hat i's minus theta hat. And we can see that in this case, the Jackknife bias estimate is equal to negative 0.35. And this is quite close to our theoretical value of negative 0.04. So one question you might have is, why do we multiply the Jackknife bias estimate with n minus 1? Let's see an analytic derivation of this. Previously, we have learned that the bias of the MLE sigma hat squared is given by negative sigma squared divided by n. For each Jackknife sample, so the theta hat i's, when we calculate the theta hat i's, we are using n minus 1 ID samples. So in this case, the bias for each of the theta hat i's should be negative sigma squared divided by n minus 1. So nothing is changing here except for the sample size. So you can see that the expectation of the bias estimate using jackknife is equal to n minus 1 times the expectation of theta hat bar minus theta hat. And this is equal to n minus 1 times the expectation of theta hat bar minus theta minus the expectation of theta hat minus theta. We are just adding the true theta, which is a constant, and subtracting it. So everything else remains the same. You should notice that here, the expectation of theta hat bar minus theta is the bias of theta hat bar for estimating theta. And similarly, the expectation of theta hat minus theta is essentially the bias for theta hat. And we know that in this case, the bias of the theta hat bar will be given by, because it's a sample mean of n theta hat i's, the bias will be equal to the bias of the theta hat i's, which is negative sigma squared divided by n minus 1. And the bias of theta hat is just this guy. So negative sigma squared divided by n. So after working out the arithmetics, we'll be able to see that this thing evaluates exactly to negative sigma squared divided by n, which is the theoretical bias of the MLE with sample size of n. You can see that in this case, our jackknife estimator for the bias of the MLE is unbiased.